In a prior video, we have introduced the concept of the chemical potential. And that is an extremely important concept because it's going to govern our work on thermodynamics for the rest of the semester. All right, so to recap what the chemical potential is, what we're interested in now is mixtures of various substances, either in the gas phase or in solution. And we're going to try to understand the properties of those mixtures. Now, stability is going to be predicted by the molar Gibbs energy or the Gibbs energy. So when you actually have a mixture of two components, the way to write the total Gibbs energy of that mixture is just going to be the contribution per mole of each one of the components multiplied by the number of moles. This contribution per mole to the Gibbs energy of each of the components is what we call the chemical potential. And an easy way to understand that concept intuitively is to assimilate it, attribute it to chemical punch. Something that has a high chemical potential has more ability to elicit a change. Okay, so these are going to be key properties in our study. The question that we asked in this video is what does that chemical potential depend on? Well, they are molar Gibbs energies. The chemical potentials are molar Gibbs energies, and we actually already know that the molar Gibbs energy depends on pressure and temperature. That's what we studied in the last chapter. Now, when we have mixtures, there's going to be a third variable on which they depend, and that is going to be concentration. Obviously, something that is highly concentrated is going to have a higher chemical potential than something that is very dilute. Okay, so in this video we explain how the chemical potential changes with concentration for a gas, because gases are the easiest substance to study. Okay, so the question is, how does the chemical potential change with concentration for a gas? Well, a couple of videos ago we explained that there are various ways to express concentration for a gas. One of them is to use mole fractions, and another way is to use partial pressures. We actually know how the molar Gibbs energy of a gas depends on the partial pressure because we are very good with this expression that tells us the dependence of the molar Gibbs energy, which is no other thing than the chemical potential on pressure. Okay, so now because we can use pressure to express the concentration of a gas using partial pressures, then we actually have a way to understand how the chemical potential depends on pressure. The way we actually integrate this expression for an ideal gas was like this: RT natural log of P2 over P1, where this is just the change in the molar Gibbs energy when you go from a pressure P1 to P2 is equal to this factor. Okay? Now, if we unfold a little bit this expression, we get that this is the same thing as the molar Gibbs energy at a pressure P2 minus the molar Gibbs energy at a pressure P1 is equal to that RT natural log of P2 over P1 term. Okay? Now, when we are in a mixture, then these things we're going to call them the chemical potentials, right? So then what we can say is that, well, the chemical potential of component A, which is at a pressure P2 minus the chemical potential of a component of the same component at a different pressure, P1, is just going to be equal to this term, RT natural log of the ratio of partial pressures. Okay? And this is our first expression of how the chemical potential changes with concentration. In this case, it's gas. And again, the concentrations are the partial pressures. Okay, let's try to rewrite that expression a little bit better. Okay. One of the things that we can do is just simply rearrange the terms to make them be like this: UA P1 plus RT natural log of P2 over P1. Okay, and I'm going to just rearrange that expression or rewrite it by assuming that our pressure P1 is what we call 1 bar. Okay, so mu sub A P1 P2 is going to be equal to mu sub A at P1, where P1 is going to be 1 bar plus RT natural log of P2 over 1 bar. Okay, this 1 bar pressure is important because it's actually the pressure of something that we call the standard state. Okay? Until now, when we've calculated enthalpies of reactions or entropies of reactions or phase transitions, all of the data that we had was at the standard state. And the standard state, the pressure of the standard state is equal to 1 bar. Okay, and it has this symbol. Okay, so in this case, I'm just trying to rewrite the expression by assuming that P1 is this standard state, 1 bar. Okay, so the way that we can write this chemical potential is saying, well, that would be the chemical potential at 1 bar, which is the same thing as the standard state. Okay? All right. This expression is actually quite important, and we're just going to simplify a little bit. Essentially, what we can do next is say, well, if we eliminate this term and remove that subindex, this looks like a very clean, very nice expression that tells us exactly how the chemical potential of a component A changes with the concentration of that gas. Okay, the chemical potential of A is going to be equal to the chemical potential of A at the standard state, 1 bar, plus RT natural log of the partial pressure at this particular condition divided over 1 bar. This is a very, very clean expression, and again, it applies to a gas, so we can write here the gas subindexes. And it's very important that you start to get familiarized with the shape of this expression, because most of the chemical potentials that we're going to be writing from now on, beyond the gas, so for a solute, a solvent, in a solution, they're all going to have this form. They're not going to have exactly the same terms, but the form is going to be very similar, right? So it's quite important that you guys start to get familiarized with that expression. Now, let's actually try to delve a little deeper into what this term is. Okay? A way that you can actually understand this expression is to say, look, the chemical potential of my substance at a particular set of conditions is equal to the chemical potential at a reference, which in this case is a standard state, plus a correction from the fact that you might not be at the conditions of the standard state, right? So this actually seems to be just a correction that tells you how far away you are from the reference state, in this case the standard state. Okay, so let's actually take a little bit of a closer look at what that correction looks like. All right, let me remind you of some properties of the logarithms. Okay, the natural log of a number x is positive when that number x is larger than 1. The natural log of x is equal to 0 when that x is equal to 1, and the natural log of x is negative when that number is between 0 and 1. Okay? All right, so let's see about this. Suppose that we're interested now in the chemical potential at 2 bar, okay, where 2 bar is greater than the pressure of the standard state, which is 1 bar. When we look at that expression, then we'll have 2 bar over 1 bar. That will be the natural log of a number that is greater than 1. Okay? That means that this natural log term is going to be positive. Right, so in the end, what that tells you is that, well, the chemical potential at 2 bar is going to be equal to the chemical potential at 1 bar plus a positive correction, meaning that the chemical potential at 2 bar is going to be greater than the chemical potential at 1 bar. And that makes perfect sense, because we know that the chemical potential should increase with concentration. Right, a gas at 2 bar is going to have more chemical punch than that same gas when the partial pressure is just half of that 1 bar. Okay? Likewise, we can now assume what happens to this chemical potential, what is the comparison between these two terms when you make the partial pressure less than 1 bar. Okay, so let's assume that we're interested in comparing the chemical potential at half bar to the chemical potential at the standard state, which is 1 bar. Okay, if we plot here 0.5, then we will be in this case in which my number is going to be between 0 and 1. In that case, the natural log is going to be less than 1, negative. Okay, and what that means is that the chemical potential at half bar is going to be the chemical potential at the standard state 1 bar with a negative correction, meaning that this chemical potential will be lower than the chemical potential at 1 bar. And again, that makes perfect sense, because when you decrease the concentration, then your chemical potential should go down. Okay, so we clearly see how this expression for the chemical potential of a gas bears down our expectations of what should happen to the ability to make a change when you change the concentration. This is the simpler case for a chemical potential, and then what we're going to be doing next is try to see how these chemical potentials are written not for a gas, but for the solute and the solvent in a solution.